Now, okay, so let's continue our problem. The thing that we are trying to demonstrate is the addition theorem for spherical harmonics. Of course, we didn't yet define what spherical harmonics are, but we talked somehow about the orthogonal functions and their orthonormality, how we can obtain, given an inner product, a definition of the inner product, how we can obtain these orthogonal functions, etc. Now, what we are doing now is we assume we have a point charge located at r prime, and we already know what the potential is, but we are trying to obtain another expression for the same potential using separation of variables in spherical coordinates. Now, our aim in trying to obtain a different expression is that we already know the uniqueness theorem. So no matter which expression, how our expression looks like, it has to be equal to 1 over r minus r prime. And in spherical coordinates, we will be basically, in separation of variables in spherical coordinates, we will be basically obtaining an expression for the potential, which will be a sum of the product of a function that depends only on r, and with coefficients that depend on r prime. So we will be able to separate each one of these components, these coordinates. So that is our aim. And we wrote this Laplacian spherical coordinates, and I just wanted to make a change of variable rather than dealing with the angle theta. I wanted to deal with cosine theta. And cos z just takes value between -1 and 1. So this is what the Laplacian looks like in terms of r, phi, and this cosine theta. And I assume this is our ansatz, let's say, and I will be looking for such a function. So with this identification, I know that the Laplacian of phi divided by phi, this will be equal to 1 over r squared del by del r. Now it won't be a partial derivative, but a total derivative with respect to r of r squared times r prime. Now here I also have the function phi and the function z, but when I divide by the potential phi, that phi and z cancels, and I also have 1 over r over here. Plus 1 over r squared d by dz, 1 minus z squared of z prime. There is a 1 over z plus 1 over r squared, 1 over 1 minus z squared, and phi double prime. This should be equal to 0. Phi double prime over phi. This is our Laplace equation in our new coordinates. Anybody who didn't hand in the homework? Now, at this point, if you just look at this part over here, phi double prime over phi, that is the only part that depends on the coordinate phi. I can change the coordinate phi independent of r and z. Nothing else changes. So if this equation is satisfied for all values of the coordinate phi, then that ratio should be a constant. Well, that constant can be both positive or negative, but if it is positive, the solution is not a periodic function. If it is negative, it is a periodic function. And I know that this function phi should be periodic with period 2 pi, because the phi coordinate is periodic with period 2 pi. So it should be negative, so that's why I call it minus m squared. And then I know that the solutions are phi is equal to e to the power I m phi. M can take values 0, plus minus 1, plus minus 2, etc. Well, I'm not writing it as e to the power I m phi plus e to the power minus I m phi with suitable coefficients. Rather than that, I'm just allowing m to take both positive and negative values. So I will be summing over all values of m, both positive and negative. Now, so I know, at least now I know one part of my solution. Let's look at the other ones. With this solution, my Laplacian takes this form, 1 over r times 1 over r squared d by dr, r squared r prime, plus 1 over r squared, 1 over z, d by dz, 1 minus z squared, z prime, and plus 1 over, no, minus m squared over 1 minus z squared. And again, this the expression in curly brackets depends only on z. And nothing else depends on z. So that function over there should be a constant, the expression in curly brackets, because if I change z, nothing else in my expression changes. So if I want my expression to be always 0, whatever the value of z is, as I change z, the expression in curly parentheses should not change. So there is another constant over there, 1 over z d by dz of 1 minus z squared times z prime minus m squared divided by 1 minus z squared. It should be a constant. Let me call that constant L plus 1. I mean, you could call it anything you like, but I will be just calling it L plus 1. So I know what this I know the equation that z satisfies now. It is d by dz 1 minus z squared z prime, and I think it was a minus sign, plus L plus 1 minus m squared over 1 minus z squared multiplied by z. This should be equal to 0. Now, how do we solve this equation? It will be, but we have to show it. Well, whenever you see such a differential equation, the first thing you can do is check what happens at the boundaries. You see z is equal, not at the boundaries, but there are some singular points. Z is equal to plus or minus 1 are singular points. So, I mean, whenever you have such a differential equation which contains some singular points, in that differential equation, the solution of that differential equation might diverge at those singular points. So that is one thing we have to pay attention to, so that nothing will diverge. Because z is equal to plus or minus 1 basically corresponds to our z-axis, and the potential along the z-axis should be finite. So that is one thing we have to pay attention to. Now you can look for a solution that is, first let me just look at the m is equal to 0 case. For this case, this is the equation we have. Now, if L is equal to 0, the solution is kind of trivial. L is equal to 0, this is 0, so Z, well, let's see. If L is equal to 0, d by dz of 1 minus z squared times z prime. This is equal to 0. So 1 minus z squared times z prime. This is equal to some constant c. Z prime is this constant c over 1 minus z squared, which I can write as c times 1 over 1 minus z plus 1 over 1 plus z over 2. If I take then the z is just c1 over 2 times the logarithm of 1 plus z divided by 1 minus z plus c2. Well, you see, our function should be finite at z is equal to plus 1 and z is equal to minus 1. So c1 should be 0. This is L for L is equal to 0. So z for L is equal to 0 should be 0. It should be some constant. Well, let's look at the case L is equal to 1. Now, for L is equal to 1, our differential equation is this one. Plus twice z. This should be equal to 0. Let's look for a solution of z in this form. A times z. Is this a solution? Well, let's see. D by dz of 1 minus z squared times z prime is a plus twice z. Is this equal to 0? If we take the derivative, it is minus 2za plus 2az. This is equal to 0. So we are done. This is the solution. How did I guess that? I know the answer. That's how I guessed it. L is equal to 2. D by dz, 1 minus z squared z prime, plus 2 times 3, 6z is equal to 0. Now let us look for a solution in the form a times z squared minus 1/3. Again, I know the answer, so that's how I guessed it. So d by dz, 1 minus z squared. Well, z prime is 2az plus 6a z squared minus 1/3. This is equal to 2a d by dz of z minus z cubed plus 6a z squared minus 1/3. This is 2a 1 minus 3z squared plus 6a z squared minus 1/3, which is 0. Again, that's the solution.
What about the second solution?
In all of them, we have a second solution, but just like in the L is equal to 0 case, the second solution diverges. So actually, we have a single solution that is finite. We do have two solutions. I mean, this is just one. What I'm writing down is the finite solution. The other solution is a divergent solution.
So the directly set is not coefficient to 0.
Yes. Now, of course, you can just go ahead and study all of them. But if you want to obtain the general solution, what you do is you start with this one. You study its behavior around z is equal to 1 or minus 1 first. So let's look at the general case. I will not do it, all of it, but I will just summarize the steps. Well, if you noticed over here, by the way, constant, this is proportional to P0, the zeroth Legendre polynomial. Here I look for a function that is linear in Z, this is P1. And this is P2. Well, the general solution is actually PL of Z. Now, to find the general solution of this expression, first, as I said, we have to study what happens close to Z is equal to plus or minus 1. So let me rewrite this first. This is 1 minus Z squared, Z double prime, minus 2Z, Z prime, plus L plus 1 minus M squared over 1 minus Z squared. Z is equal to 0. Now, I will assume that for Z close to plus or minus 1, those are the singular points. Let's see how it behaves. It should behave like Z plus or minus 1 to some power. Times, of course, there will be other coefficients. Now, the problem is, what is this power? So let's just substitute this into our expression. So it is 1 minus Z squared. Well, if I take the derivative twice, I get nu minus 1 times Z plus or minus 1 to the power nu minus 2. Minus 2Z, if I take the derivative once, nu times Z plus or minus 1 to the power nu, plus L plus 1 minus M squared divided by 1 minus Z squared times Z plus or minus 1 to the power nu. This should be equal to 0. Now remember, I'm close to Z is equal to minus 1 for the upper sign and plus 1 for the lower sign. 1 minus Z squared. When Z goes to minus or plus 1, by taking values smaller than that, this is nothing but 1 plus or minus Z times 2.
So when x will inject x z plus minus 1, so when x will.
Yes. I'm taking the derivative. This is equal to 1 minus Z, 1 plus Z. Well, if Z is close to 1, I keep the 1 minus Z, the other one becomes 2. If Z approaches the minus 1, then the first term becomes 2, the second term, I just keep it as it is, so it is minus plus. Close to the point 2. Now let us go back to our expression. So it is twice, now 1 minus Z squared, no, 1 Z, hold on, so this is, let me write this in this form, plus or minus twice 1, no, twice Z plus or minus 1. If it is the plus sign, it is plus. If it is the minus sign, it is minus. Yes. So that everything looks like Z plus or minus 1. That's the purpose. So it is plus or minus 2, nu minus 1, Z plus or minus 1 to the power nu minus 1, minus, okay, Z is plus or minus 1, or this is plus or minus twice nu Z plus or minus 1 to the power nu minus 1, plus L plus 1 plus or minus M squared over 2 Z plus or minus 1 multiplied by Z plus or minus 1 to the power nu. This should be equal to 0. Now, I'm looking at the most singular terms. So here you see the L term is to the power nu. There is a to the power nu minus 1 term. Z plus or minus 1 to the power nu minus 1 should cancel. So I have 2 plus or minus twice nu minus 1, plus or minus twice nu, plus or minus m squared over 2 should be equal to 0. Remember, although I'm only looking at the z plus minus 1 to the new term, I have infinitely many terms in my Taylor expansion. I'm doing basically a Taylor expansion. Close to z is equal to plus or minus 1. So this is 2 nu squared, and new terms cancel, plus or minus m squared over 2 should be equal to 0. Okay, for m is equal to 0, nu should be equal to 0. Plus or minus 0. Well, there's a funny thing. This is, so z of z is either a constant or z of z is logarithm of 1 plus z or 1 minus z plus a constant. Close to z is equal to plus or minus 1. Logarithm essentially is a function just like to the 0th power. So these are the two solutions we have. The logarithm one, we ignore it, we don't take it, we throw it away because it's not finite. It's the other one we take. And we know that that function, I mean, it doesn't have any, well, if nu was, let's say, a kind of a fractional power, then our function will not be analytic at z is equal to plus or minus 1, so Taylor expansion would be problematic. But we know that our function is analytic at z is equal to plus or minus 1. So we can just make a Taylor expansion which will be valid up to z is equal to plus or minus 1. So you just said this is equal to an, z to the n equal to from 0 to infinity. This is not a polynomial a priori. Then you have to look for what an should be. Just take this expression, put it into our differential equation over here, do the Taylor expansion, and then you will find some recursion relation for ans. You will be able to relate an plus 2 to an. And then you will see that unless that the series terminates, the function you obtain is infinite. When it will be infinite. So you will have to require that your function terminates. So it becomes a polynomial. So these are basically the general steps. So I will just write down the answer. Z of z is what we call the associated Legendre polynomials. Now this PL of z, we have already seen some examples. This PLM of z is, you just take their derivatives in a suitable derivative form. I mean, I don't intend to give into the details of these functions. I can give you some homework on them, but the thing we know we need is that the solutions of this equation over here, we call the solutions that are finite at z is equal to plus or minus 1 are these associated Legendre polynomials. That is the only thing we need to know. They are orthogonal functions. They form a complete set. And m can only take values between minus L and plus L. Otherwise, the function is not finite. So now we already know what our functions are. So our solution for the potential, we said that there is still the radial part which we need to determine. Well, the part that depends on z, we said that they are PL of m of z, and there are also the phi dependent part. So this is what our function looks like. And this combination you will see quite often. Well, it's basically the solution, the angular part of the solution of the Laplace equation, which you see in quantum mechanics, in electrodynamics, in classical mechanics, etc. So we give it a special name, that combination. We call that YLM. Some coefficients times PLM of Z e to power I m phi. And we choose the coefficient such that YLM star theta and phi, YL prime m prime, again theta and phi, d cosine theta, d phi is equal to Kronecker delta L prime, Kronecker delta M prime. So we choose the coefficients such that they are properly normalized and they are orthogonal to each other. So this is what we call the spherical harmonic functions. You can think of them as basically the generalization of sines and cosines to, if the angles are defined on 2 dimensions, and then you can talk about the sine and cosine of an angle. In 3 dimensions, we have 2 angles, theta and phi, or solid angle. And spherical harmonics is kind of the generalization of this sine and cosine function to 3 dimensions. They look quite similar. And they are complete, so just like in Fourier series, you can write any periodic function in terms of sine and cosine. These are also complete. Any function of the angle theta and phi, you can write in terms of the spherical harmonics. And you can use their orthogonality to obtain their coefficients. Now that brings us to the last part of our differential equation, the last one. You see, we started with this one. That part we called minus L times L plus 1. So the radial part times minus L times L plus 1, this should be equal to 0. This is the last part of our solution. Now let me just take the derivatives. This is 1 over r squared times twice r prime plus r squared r double prime. Now let me also multiply by r squared. Minus L plus 1 times r, this is equal to 0. So r squared r double prime plus twice r prime minus L plus 1 to the power r, this is equal to 0. You see, the second derivative is multiplied by the second power of r, the first derivative is multiplied by the first power of r, and the 0th derivative is multiplied by the 0th power of r. So whenever you see such a differential equation, the general solution is just a polynomial. So r should be equal to r coordinate raised to some power. Now let's determine what this power is. If you just put in if you put this in our differential equation, you get n times n plus 1 and plus 2n, no, n times n minus 1 r to the power n plus twice n r to the power n minus L plus 1 r to the power n. This is equal to 0. R is non-zero. So n times n plus 1 minus L times L plus 1, this is equal to 0. Well, in fact, this is why from the beginning that constant that appeared in the z differential equation, why we called it L times L plus 1 rather than just some number. So that the solution of the radial equation will look simpler. So the solutions, we have 2 solutions, either n is equal to L or n is equal to minus L plus 1. These are the 2 solutions we have. So this kind of completes the expression for the potential in its general form. Phi of r should be equal to a r to the power L plus b r to the power minus L plus 1 and YLM. Of course, this A can be a function of L and M. B will in general be a function of L and M. I did. You see, here I have n squared minus n. Then I add the 2n, so it made n times n plus 1 rather than n times n minus 1. So this is my general solution for the potential in spherical coordinates. My potential at a point where there are no charges. This is the solution of the Laplace's equation. So in a region where there are no charges, the potential should have this form. Now, let's go back to our problem. This was the question we had. We had some charge over here, so we assumed the sphere, and that charge Q lied on our surface. We had this region 1 and region 2. We divided our space in two regions. And in region 1 and in region 2, the potential satisfies the Laplace's equation, so the potential should lie as the above expression in region 1 and region 2. Now let's write down the potential in region 1. You see, in region 1, and okay, let me write this L and summation over L goes from 0 to infinity. M goes from minus L to plus L. Those are the limits of my integration. Now, in region 1, there is a point at origin which has r is equal to 0. My potential should be finite at r is equal to 0. But if you look at the B terms, B term, it goes as 1 over r, 1 over r squared, 1 over r cubed, etc., which all diverge at r is equal to 0. So at the in region 1, the B terms should not be there. Their coefficient, all of them should be 0. And I'm left with only the A terms. So this is equal to L and M, A L M, R to the L, Y L M omega. Do you agree? Well, you see the B terms, they are proportional to inverse powers of R. In my region 1, there is a point R is equal to 0. But my potential should be finite at R is equal to 0. But B terms diverge at R is equal to 0. So they cannot appear in region 1. If we go to region 2, then it's the other way around. The A terms have positive powers of R which diverge at infinity. But I know that at infinity my potential should be 0. B terms, they all go to 0, so they can stay in my expression, but A terms should not appear. So in region 2, my potential is Lm, BLm, 1 over r to the power L plus 1, YLm omega. So I have my solution in region 1, and I have my solution in region 2. Now we have the boundary conditions, the boundary separating region 1 and region 2. And those are the potential should be finite. No, not finite, continuous. That is phi 1 should be equal to phi 2 when r is equal to capital R. This is the continuity of the potential. Well, that tells me that sum over ALM, capital R to the L, YLM omega, should be equal to BLM, 1 over R to the power L plus 1, YLM omega. Well, YLMs are orthogonal functions and complete. So if these two expressions are equal for all values of omega, well, when I say omega, I'm meaning a particular value of theta and phi, their coefficients should be equal. So ALM, r to the power L, should be equal to BLM times 1 over r to the power L plus 1. So I have these two sets of coefficients, ALM and BLM. Then, in order to determine their values, I have to have two sets of equations. This is one set of equations relating ALM and BLM. Now I need to find the second set. The first set I obtained by the continuity of the potential at the boundary. Now the second one, I know that the normal derivative, or let's say at the boundary, on the boundary, delta E, the change in the electric field, should be equal to sigma, 4 pi sigma, times the normal vector. Well, the radial component of the normal vector is the radial direction. Now, the radial component of the electric field is minus d phi by dr. So ER, the radial component in the first region, is equal to, when R is equal to capital R. You see, in the first region, this is my potential. I have to take the derivative with respect to R, the radial component, and multiply it with a minus sign. So this is minus sum over A, L and M, A, L, M, L times R to the power L minus 1, Y, L, M, omega. And in the second region,